Thank you very much for organizing this and for inviting me. So it's my pleasure to speak here. So I will talk about basically my goal was to give an overview of the classical theory of free boundary problems, and then in the last lecture to present some very recent results that we obtained with Alessio Figali and Joaquim Serra. But as I said, I wanted to start from the very classical theory that was developed in the 70s and 80s by Caffarelli. And I will talk about two free boundary problems, as we will see. So basically, I don't know if you can see the slide. I hope you can. Basically, the goal is to understand the regularity theory for these two classical free boundary problems, which are the obstacle problem and the Bernoulli or one-phase free boundary problem. Okay, so these are two of the most classical or probably the two most famous elliptic free boundary problems, and the regularity theory was initiated by Caffarelli and others in the 70s and 80s, and still today is a very active field of research, both for the obstacle problem and the Bernoulli problem. We have had very important recent results, and then I will present some of them here in the last lecture. Okay, so basically both problems come from the calculus of variation, if you want, in the sense that we minimize energy functional, okay, in which there is a non-smooth behavior at u equals 0. Okay, so the solutions will have a discontinuous behavior when u equals 0. Okay, and then it will have like two different parts. One in which u is positive, and then it solves a PDE, and then the other in which u is simply 0, the constant equal to 0, and then there will be an interface between them. Okay, and basically this is the picture. Okay, so one part in which u is 0, one part in which u is positive. This red curve would be like the boundary of the fixed domain. So we have a fixed domain that could be the full space maybe, and then the important part is this transition, this interface, which is called the free boundary. Okay, because this is part of the problem as well, and this is what we call the free boundary, and this is what we want to understand basically. Okay, so these type of problems, so these two problems in particular, but also some others that are related or similar, they appear in a variety of settings. Okay, but in particular these problems, the same exact problem appears in very different settings, from physics, probability, biology, etc. And then our goal is to understand them from the mathematical point of view. Okay, and prove to see what is the best we can say about solutions and about free boundaries. Okay, and the regularity theory for these two problems uses many ideas from geometric measure theory, and in particular there is a strong analogy with the theory of minimal surfaces. Okay, so it's not that we use results from minimal surfaces, but really the overall strategy, and there is a strong analogy basically with the theory of minimal surfaces, and therefore I want to very briefly mention what is so let's do it like this, with the theory of minimal surfaces. Okay, so let me very briefly describe what is the classical theory of de Giorgi for minimal surfaces in Rn. So these are hypersurfaces in Rn, and basically, so given a domain omega, we look for a set, okay, that would be this set E, such that is fixed outside. Say you can think it's fixed on the boundary. So this is like the boundary datum. Okay, so this is fixed here. And then we look for so if this is 2D, this would be like a curve, but in general, we are in a range, so this would be like the hypersurface. So we are looking for a domain here such that its boundary is a minimal surface. Okay, so E, this set E that we are looking for, it coincides with this set E0 outside omega, and this set E minimizes the perimeter. Okay, so we minimize the perimeter inside omega among all sets that coincide with this boundary datum. Okay, and this is the classical problem that was studied by de Giorgi and many others. And basically, the regularity theory is as follows. Basically, we have two main steps. The first one is quite easy. but not so easy. So this is the existence, okay, and I will not discuss it very much, but basically there is always a minimizer and is a set of finite perimeter. Okay, so this is why the Georgi and others developed the theory of sets of finite perimeter, or Cacciopoli sets, and then you get existence. Okay, but then once you have a minimizer and it's a set of finite perimeter, you would like to understand the regularity. To what extent this is a nice hypersurface? So can you prove that this would always be a smooth hypersurface, for example, or it might have singularities? Okay, this is the kind of question that we want to answer, and then describe singularities, etc. Okay, and for minimal surfaces, the best result, I mean, in it is sharp, so the best one can say is that in dimensions n less or equal than 7, so if the space is up to R7, then minimal surfaces constructed in this way are always infinity. Okay, so you do this, you minimize perimeter, you get a set of finite perimeter, and then it turns out that this set, because it's a minimal surface, is always infinity. Okay, and this is a theory that I mean, this is the outcome of many important results in this field. And then moreover, in dimensions 8 or higher, we might have singularities. So the singularities do exist. They exist only in dimensions 8 or higher. And the best we can say is the following, is that in higher dimensions, 8 or higher, so minimal surfaces are infinity, possibly outside a set of singular points, sigma, and we have a dimension bound for the singular set, okay, which is that it has the Hausdorff dimension at most n-8, and this is sharp. Okay, so this is the theory of minimal surfaces, and then the question is, well, how do we prove such regularity? Because as I said, for free boundary problems, we would have we would use a similar strategy. Okay, so and what is this strategy? So the overall strategy, without entering in any detail, but just to have a strategy to start with, is the following. So first, you notice that the problem is a scale invariant. Okay, so in a sense, if you have a minimal surfaces and you zoom in, you rescale, then it's still a minimal surface. It solves the same problem. Okay, so if you have a minimizer in a ball, you rescale it, it's still a minimizer locally, and for any rescaling, this is true. So we can study blowups. What is a blowup? You just rescale more and more. You zoom in and take the limit. This is what we call blowups. Then once we consider blowups, we get an extra information, which is that we have a monotonicity formula, okay, and it tells us that blowups are always cones. So blowups have a special structure because of a monotonicity formula. Okay, so we improve, and then we can hope for a classification of blowups because we have some more information. Okay, and then the classification of blowups turns out to be this one. So this is a deep result from Jim Simons, and it says that up to dimension 7, all minimal cones must be half spaces. Okay, so this is the classification of blowups. Okay, and then once you have the classification of blowups, you notice that because when you zoom in, you converge to a half space. So it means that when you zoom in, the minimal surface looks flatter and flatter. Okay, because in the limit, you know that it's completely flat. So you take this information that you can make E or a rescaling of E look as flat as you want locally at any point, right? So, and then there is the probably the most important step in the theory, which is this is the classical result of the Georgian 61, I think, in which he proved that if you have a minimal surface that is flat enough, so there exists an epsilon such that if you are epsilon flat, then it is C1 alpha. So the surface is C1 alpha. And this is crucial. So there are two crucial steps, which is the classification of blowups, well, the monotonicity formula also, but the classification of blowups, and then the flat implies C1 alpha. And then you need one last step, which says that actually, once you are C1 alpha, you are then infinity. Okay, so this is the theory for minimal surfaces. And this strategy is very similar, or is analog to the one we use in free boundary problems. Okay, and actually, up to some certain extent, we can treat both problems at the same time. Okay, so we will see that both problems have some similarities. Okay, and then we will see what are the main differences, because the results are actually quite different, but the beginning of the strategy is quite parallel. Okay, so what I want to do is to start seeing the parallel between the two problems, and then proving some of the things at the same time. And then we will go to the classification of blowups, in which the two problems completely separate in two different directions. Okay, so the obstacle problem, basically, in its simplest formulation, is to minimize this energy functional. Okay, so this denotes the positive part of U, and this problem is equivalent. So if you don't want to minimize the positive part of U, it's called the obstacle problem, because you can also minimize simply this without the positive part, but among all functions that are non-negative. So you constrain the problem. Okay, so this is a constrained minimization problem in which you minimize smooth energy functional, but among all functions that are non-negative. Okay, but it's equivalent to minimizing this. Okay, it's easy to see. It's an easy exercise to show that it's equivalent to minimizing this non-smooth functional among simply all function in H1. So you get these non-smooth energy functionals that we minimize. So this is the positive part of U, and this is the obstacle problem, while the Bernoulli problem is even more singular in a sense. So the functional is more, it's actually discontinuous. So this has a discontinuous derivative, but this is a characteristic function. So this is discontinuous itself. And then this is the energy functional that we minimize in the Bernoulli problem. Okay, so basically you measure the set in which U is positive and you penalize it. So you prefer I mean, you pay for all the region, for the area of the region in which U is positive here. While here, it's the positive part of U. So it's in both cases, you have this picture, one region in which U is 0, okay? So because it's cheaper to be 0, in a sense, when you are close to 0, it's cheaper to be 0. So there will be one region in which U is equal to 0 here, and one region in which U is positive. Okay, of course, this will depend on the problem, but the picture is somehow the same. Okay, and then this is the free boundary. That is the main thing that we want to understand. And of course, there is always some fixed boundary data here, but I will not consider it very much because all regularity results are like local, in the sense that if you are minimizer in B1 with any boundary data, then we prove some regularity result. Okay. And well, so this is the picture we have for the functional. This is the positive part of U. This is the characteristic function of U. And then when U is 0, you don't pay the price, say, in the functional. But of course, you also pay for the gradient of U. So this is like you need to balance, in a sense. You don't want the gradient to be very steep, but you want U to be 0 as much as possible. And then this is the picture that you always get. Okay. And so notice that these two functionals, so in terms of existence, they have a different behavior in terms of existence. Why? Well, because this is a convex energy functional. Okay, so this is a convex function. So this is a convex energy functional, while this is non-convex. Okay, so this is convex energy functional, this is a non-convex energy functional, and therefore we will have the following: that for a convex energy functional, we always have uniqueness of solutions, while here we don't have uniqueness in general. Okay, and therefore we can still prove that there exists a minimizer, but it might be not unique, and there might be other critical points. For example, there might be several critical points, but only one of them is the minimizer, etc. Okay, so there is a more rich family of solutions maybe in this context, while here is more similar to I don't know, harmonic functions in which you always have only one. So for this, as we will see, we will study solutions. We will not use that they are minimizers, while here we will need, for the regularity theory, we will need to use that we are minimizers of the energy functional, because critical points are less regular. Okay. So we have uniqueness of solutions here. In general, we have non-uniqueness of solutions here, but we always have a minimizer, at least one. Okay, and then what is the PDE that you satisfy? So if you take a minimizer or of this energy functional, it will solve this PDE. So at least formally, this is immediate to check. I mean, you really by the direct method of the calculus of variations, there is a minimizer, and then you see what is the Euler-Lagrange equation, and it's this one. So the Laplacian equals to the characteristic function of the set where U is positive. So this is a nonlinear problem, but the Laplacian is bounded, for example. Well, okay, and it's discontinuous. It's a characteristic function. Okay, so this is the PDE satisfied by U. While here in this context, this is a bit more tricky. It's a bit more delicate to see what is the PDE satisfied by U. But basically, the derivative of this is like a Dirac delta on the free boundary. Okay, so the function will be harmonic whenever it's positive. It will be 0 whenever it's 0. And then here, this is basically a Dirac delta. The derivative of this is a Dirac delta on the free boundary. So what you get is that the gradient of U has modulus 1 along all the free boundary. Okay, so at least formally, this is somehow easy to check. And this is the PDE satisfied by U. Okay, so we have the two different PDEs that from the PDE, you can see really that even though the functionals are somehow similar, the PDEs are quite different. Okay, so here you really have a PDE. While here you really need to write it as a free boundary problem with harmonic function inside the set value is positive with some free boundary condition here. Okay. Now, what can we say about these solutions? Okay, so if we take this as a PDE or this one, minimizers of this, what can we say about the solutions U? Okay, and the first step, for example, in the obstacle problem is saying, well, first, the Laplacian is bounded. So whatever this characteristic function is, this is bounded. So because the Laplacian is bounded, solutions are C1 alpha for sure. Okay, this is from theory for linear equations. So solutions are C1 alpha for every alpha strictly less than 1. Okay, but then we can improve this a little bit. And it's that the optimal regularity is that solutions are C1 1. Okay, so the Laplacian is discontinuous. So this is, of course, optimal. But one can prove this, that solutions are C1 1 with an estimate in terms of the L infinity norm of U, for example. While in the case of the Bernoulli problem, minimizers of this are Lipschitz. So notice that first U is 0 and then the gradient is 1. So Lipschitz is optimal. Okay, so Lipschitz is the natural optimal regularity in this context, and we have this estimate in terms of the L infinity norm as well. So these are the optimal regularity estimates for U. And this is not so difficult to prove. So this is not the difficult part of the theory. And let me briefly mention also that we have a non-degeneracy property in both cases. So here we have if 0, say the origin is a free boundary point, then the supremum of U in BR is really comparable to R squared. So from above, this is really the optimal regularity. So you have a function that is 0 at the origin with 0 gradient because it's a C1 function. So in particular, it has 0 gradient, it's a minimum. And then it grows by C11 regularity, it grows at most like R squared. Okay, but then on the degeneracy says that it grows at least also like R squared. Okay, so really, this is really the behavior of solutions near all free boundary points. And the same happens for the Bernoulli problem. Okay, so if the origin is a free boundary point, then we have that the supremum of U is comparable to R. So it grows linearly away from the free boundary. Okay, so from above, this is the optimal regularity, and from below, this is what we call non-degeneracy. Okay, so we have some information that will be useful later on. That is the supremum of U, the L infinity norm of U in small balls is comparable to R or R squared. Okay, then this is the picture. Like U grows like similar to a parabola here, while similar to a linear function here. Okay, so this is the picture to have in mind around free boundary points. Now, how do we prove this? Well, for the bound from above, we simply use that U is non-negative. Okay, and the harmonic inequality with an L infinity right-hand side already tells you that supremum is bounded by infimum plus R squared, the L infinity norm. Okay, but the infimum is 0, the L infinity norm of the right-hand side is 1, so you get C R squared. Okay, so this is very easy. And for the lower bound, you basically apply, I mean, I don't want to enter into details, but you basically apply the maximum principle to the function that is defined by this, which is U minus a parabola. Basically, you apply the maximum principle and you get, after a small trick, you get the non-degeneracy from below. Okay, so this is, you see that this is very, very short, and you get the optimal regularity and the non-degeneracy with constants that depend only on the dimension. Okay, what about the Bernoulli problem? Well, in the Bernoulli problem, basically you have two observations that prove the bound from above and below. So basically, if U is a minimizer and U of 0 is bigger than a constant, then if the constant is large enough, I mean, there exists a constant depending only on the dimension, such that if U of 0 is bigger than a certain constant, then U is positive in all B1. Okay, so this is a easy exercise. You can even prove it by compactness. And rescaling this, you get that if the supremum in BR is bigger than C times R, then you would have that U of 0 is positive, which is a contradiction if you assume that. So this means that if U of 0 is 0, so that it's a free boundary point, then the supremum is less than or less or equal than CR. Okay, so this proves the upper bound. Okay, so this is the upper bound. And for the lower bound, you first prove that if U is positive in B1, then actually U of 0 has to be really positive with a constant, with a universal constant, because otherwise it's cheaper to go to 0. Okay, so if you have a positive solution, a positive minimizer, it really has to go way above 0. And then this implies that U is bigger than the distance to the boundary. And then with a bit more work, this yields that the non-degeneracy is that the supremum of U is really bigger than C times R. Okay, so this is basically the rough idea of the optimal regularity and non-degeneracy for both problems. Okay. So I didn't say it from the beginning, but if you have questions and you want to stop me, I will be happy to answer. Or if not, you can ask any questions at the end of the lectures, of course. So this is the optimal regularity and non-degeneracy. And now, so we proved basically, so once you have this upper bound, then the Lipschitz estimate is easy just by interior estimates, and the same happens here. Okay, so this and this follow from these upper bounds. Okay, so, and then why is this so useful? So the optimal regularity and then non-degeneracy, so these two bounds here and here, why is this so useful? Well, because now if U is any solution, and then say that the origin is a free boundary point, then this rescaled function is a solution to. So this rescaling parameter R squared, you cannot choose it. I mean, really, R squared is the parameter that goes well with the equation. Okay, because the Laplacian, you get an R squared in front, so that if you were dividing by R squared, the R squared cancels. So this is still the Laplacian of UR. And then the characteristic function, well, you get the same equation, and then the R squared doesn't matter. Okay, but R squared is really the parameter for which the equation is invariant. Okay, and then we are happy because these rescalings really go well with this non-degeneracy and optimal regularity properties. And the same happens here. So minimizers of this, you have to rescale them by this parameter R, so that they are still minimizers. So that, I mean, you can, it's an easy exercise that if you take a minimizer of this and you rescale in this way, then UR is still a minimizer of this in the ball B1 over R, in a large ball. Okay, so the equation or the functional has a natural scaling, which is, in the case of the obstacle problem, is R squared. In the case of the Bernoulli problem, is R. And in both cases, we are lucky that, well, we have optimal regularity and non-degeneracy that go well exactly with this power, with the natural scaling power for the problem. Okay, so this is very important. So now, if we have a solution and we rescale it around the origin with the natural scaling, we get still a solution. Plus, what this tells us is that this rescaled solution will have L infinity norm that is comparable to 1. So the L infinity norm of this is bounded by two constants, large C and small c, that they don't go to 0, they don't go to infinity. Okay, so this is very important here and here. So we have scale invariance for the problem, and these rescalings, they have a controlled L infinity norm. Okay. Also notice that if you have a controlled L infinity norm, then simply by estimates, by these optimal regularity estimates, you have control in the C11 norm here or in the Lipschitz norm here. So everything is controlled and nothing goes to 0. Okay, so this gives the necessary scale invariance to consider blowups. Okay, so all this is necessary even before starting to do any blowup. Okay, which is what we want to do if we want to try to mimic the theory of minimal surface, in a sense, to do the analog of the theory of the regularity theory for minimal surfaces. We want to do blowups, but first, before doing any blowup, we needed all this. So we needed to see what is the natural scaling, then prove the optimal regularity and non-degeneracy, so that these scalings have a controlled growth and they don't converge to infinity, they don't converge to 0. Okay. So this is the common feature in both cases. And then we can consider blowups, right? So the result is then as follows. So this is like proposition. If you have a free boundary point and you consider the natural scaling for the function, then the rescalings converge in C0 alpha norm or in C1 alpha norm, depending on the problem. They converge along a subsequence to a blowup U0. So they simply converge to something. They converge to a function that is C11 here, or it's Lipschitz here, and this is what we call the blowup. Okay, so in particular, the blowup is non-zero and it's not infinity. So they really converge to something. Okay, so this is good. And moreover, this blowup U0. So here, this blowup U0 is a non-trivial global solution to the obstacle problem. And in this setting, the blowup U0 is a non-trivial global minimizer of the energy functional for the Bernoulli problem. Okay, so they really preserve, so blowups really preserve the equation and the fact that they are minimizers of the energy function. Okay, and this is very important because then we can use more properties about this blowup. So what is the proof of this? So this is really simple because we already have all the ingredients, right? So we already said that these functions, these rescale functions, have L infinity norm comparable to 1. So by C11 estimates for the optimal regularity, so you can also have it in B2, so that this is in B1, you have that the C11 norm of UR is controlled, not only in B1, but in any ball, actually, because the domain gets larger and larger. So you can do this in every ball in Rn, in every compact set. And once you have this, then by Arzelà-Ascoli, these functions UR up to a subsequence, they will converge to a function U0. That is what we call the blowup. Okay, and then passing the equation to the limit is easy once you have, I mean, simply by uniform convergence, it's not difficult to see that you can really pass the equation to the limit and get that you get a global solution to the obstacle problem. Okay, and same here. It's not difficult to have that thanks to uniform convergence, you pass the equation to the limit. Okay, so this is the proposition that gives us, thanks to the scale invariance, we get blowups. So we can consider blowups. And then the question, the important question is, well, can we classify blowups? Okay, so this is really a much more difficult question. So even though we can consider blowups, the very difficult question is, can we classify them? Okay, and then after that, we can see if we can try to use this classification of blowups to deduce something about the free boundary. But first, we need some classification of blowups. Okay, so this is the next question. And for this next question, there is first a piece of information that is common in both problems. And then really the theorem of classifying blowups will be different in the Bernoulli problem or in the obstacle problem. Okay, so let's see what is the still one more step that is a common piece of information that we have for both problems. And it's the following. So which is for minimal surfaces, we had a monotonicity formula. I said, if you have a surface and you consider blowups, then we have a monotonicity formula that tells us that all blowups will be cones. Okay, so blowups will have this scale invariance, they will be cones. And then the question here is, can we find something similar here? And then, of course, this is not something that you can have for any problem. For any free boundary problem, in many cases, there is no monotonicity formula. But in this context, because these are nice free boundary problems in which the Dirichlet energy appears, so we have like harmonic functions, so we can hope for a monotonicity formula. Okay, so it's not clear that we will have one, but one can at least try. Okay, and it turns out that we do have a monotonicity formula. Okay, and then this is the quantity. So this is, I call it W because this is due to Weiss. Weiss found that this quantity, okay, so if you forget for a second about this term, the second integral, so this first term is very, very natural. Okay, so this first term is really the energy of UR at scale 1, or if you want, the energy of U. Okay, so this is exactly the energy functional. This is the energy functional at scale R, so BR, with the natural scaling parameter here. Okay, so this is what Weiss found, was that if I take the energy at scale R, okay, which is the same by scaling invariance, this is the same as the energy of UR in B1. So if I take this, well, this is not monotone, okay, but if I subtract something, then this is monotone. Okay, so this is what we will see, that this quantity is monotone. And then for the Bernoulli problem, it's the same. You really take, and this is also due to Weiss. So if you take the energy functional at scale R and you divide by the natural power of R, so there is only one power of R that can go here, and this is really also the energy of UR at scale 1. So this is very natural quantity. So this is maybe not monotone, but once I subtract this, then this will be monotone. Okay. So this quantity and this quantity satisfy that the derivative is non-negative. Okay, so the derivative of this is non-negative, the derivative of this is non-negative. Moreover, you see what is here inside the square. Well, so this will be constant if and only if this is 0, or if this is 0. Okay, but then this is 0 if and only if the function is homogeneous of degree 2. And this is 0 if and only if the function is homogeneous of degree 1. So this is really nice. Okay, because this will give us a lot of information. And this is what I was saying, that this quantity, this monotonicity quantity, W at a scale R, so this is constant in R if and only if U is homogeneous of degree 2. And this is constant in R if and only if U is homogeneous of degree 1. So this is also an easy exercise that, I mean, this being 0, so it's constant if and only if the derivative is 0, and the derivative is 0 if and only if this thing inside the square is 0. And then this is an easy exercise to show that this being 0 implies, so it's equivalent to saying that the function is homogeneous of degree 2 and of degree 1 here. Okay, so this is the Weiss monotonicity formula for both the obstacle problem and for the Bernoulli problem. Okay, and as a corollary, we get that blowups are homogeneous. So why is this? Because basically in both problems, so this is like a common proof in both problems. So the quantity it has some nice scale invariance. Okay, so what happens if I apply this monotone quantity, this quantity that I want to prove it's monotone? So what if I apply it to the function UR at the scale rho? Well, then by scale invariance of everything, you can check. This is also a simple computation. You check that if you apply the monotone quantity at the function UR at scale rho, this is the same as the quantity applied to the function U at scale rho times R. Okay, so the powers of R are crucial here. Okay, so these powers of R are really the only ones for which this happens. So you want quantities that are scale invariant. Okay, and these both quantities are. Okay, so they have this nice scale invariance that when you apply the quantity to UR, you can really translate it into the power, the quantity of U, but at scale rho times R. Okay, then once you have this, you let R go to 0. Okay, so letting R going to 0, this converges, so this right-hand side converges to this one. Okay, so rho is fixed, and then UR converges to U0. So this converges to this. Okay, for every row, for every fixed row, this converges to this. And now this U is fixed, while now R goes to 0. So this one converges to this. And notice that the limit exists because it's monotone. This is where we use the monotonicity. Okay, so that this limit exists along the sequence R going to 0. So the W of U rho times R converges to this. So the energy, I mean, this kind of energy of U at 0. But now I'm saying this is true for every row. So the quantity, the Weiss quantity at the function U0 for every row gives the same value because this is independent of rho. Okay, so in particular, this function of rho, the function of rho that is the monotonicity formula applied at the blow-up U0, this is constant. But then if this is constant, we get that the blow-up is really homogeneous of degree 2, and then in this case, homogeneous of degree 1. So this is how monotonicity formulas are important here, because they give us some piece of information that it's very, very difficult to obtain them in any other way if you don't have this monotonicity formula, right? So they give us right away that blow-up will be homogeneous. Okay, so you only need to find, and this is the tricky part, of course, you need to find the right quantity. Okay, but once you find the right quantity, then this gives us that blow-ups are homogeneous of degree 2 in the case of the obstacle problem, and blow-ups are homogeneous of degree 1 in case of the Bernoulli problem. Okay, so this gives us some hope to then classify blow-ups. Okay. So if I go a bit too fast, or you have questions about this, as I said before, just let me know. Okay, and then I'll be happy to answer any questions. So how do we prove this monotonicity formula? Okay, so let's take the one of the obstacle problem and do the computation a bit quickly. So I go a bit fast because this is really the classical theory, and I want to have time to get to the end and present some new results. But I think it's still useful, even if I don't go over all details. It's still useful to know the theory. How do we prove a monotonicity formula? How do we get that blow-ups are then homogeneous? Okay, so the first thing, as I said before, is that this quantity, so the powers of R are chosen so that this is true. Okay, so the Weiss quantity at scale R is the same as the Weiss quantity for UR at scale 1. Okay, so this is the same as, and more generally, you have this, okay, which is what we used before, that the UR at scale rho is the same as U at scale rho R for this energy. Okay, but then if I want to compute the derivative in R of this, it's probably easier to compute the derivative in R of this, because now the domain of integration is fixed. Okay, so instead of computing the derivative in R of this quantity, I will compute the derivative in R of this quantity, which looks better. Okay, and then basically, if I rename UR to U, basically, I mean, UR, if I want to compute the derivative of U at rho, it's the same as computing this, the derivative of the energy of UR at here. So basically, it's the same. Everything boils down to computing the derivative at R equal 1. Okay, maybe for a rescaled U, but you can always rescale U, and then everything is the same. Okay, so I will compute this. Okay, and then notice that the derivative in R of UR when R equals 1 is exactly this one. Okay, so this is by definition of UR. So remember, UR was u at Rx divided by R squared. And then the fact that the denominator is R squared gives you these two. Okay, while in the Bernoulli problem, you will get a 1 here because the denominator is R instead of R squared. Okay, but this is really by definition of UR, you get this. And then also the derivatives in R commute with the gradient, which is a derivative in X. So we can start computing. So we want to compute the derivative in R at R equals to 1 of this. Okay, so we take this form of the Weiss energy functional, and then we compute. I take only the energy so that you see that it's the natural way to do it, I think. So you take only the energy term, which because it's the natural term in which you want to check if it's monotone or not. You take the energy of UR and then compute the derivative and see what we get. Okay, and then you compute. This is really a computation, and you get gradient U times gradient of this, then plus this, which is the derivative of U. Okay. Okay, so this is really computing a derivative. The positive part of U just disappears because U is not negative. So a posteriori, this is really the functional. And then this is the computation. And then you integrate by parts. I mean, of course, I don't want you to know all details. It's just really computation. You compute this, you integrate by parts here, you integrate by parts here on the, you get a boundary term. And then this term goes here. So I only integrated by parts once. I put this gradient here to get a Laplacian. Okay, I get a boundary term, and this term stays the same. Okay, and then the Laplacian is 1 whenever U is positive, because when U is 0, simply this is 0. So this we can substitute by 1. The normal derivative on the boundary of the sphere is really equal to x times gradient U. So I substitute all these terms. And then I get on the boundary, I get x dot grad U times this. And then on the interior of the ball, I don't get anything because this Laplacian is 1 and I have a minus here. So I get the integral of this. And then this term is exactly the one that I had here. So this term cancels with this. So I get only the term on the sphere, and the term on the sphere is exactly this one. Okay, so I can now write it as a square, right? Because this looks nice in the sense that if I add and subtract 2 times U on here, I can write it as this thing square, this term square, plus 2U times this. Okay, and this is what it is. This is the derivative of the energy functional of UR. And then I took the derivative in R, I got these 2 terms. This is a square, which is really nice. And this is an extra term that I don't like. Okay, but now this is where this term enters into play. So now if you can write this as the derivative of someone, then you're done. Because then this someone will be monotone. Okay, and this is exactly what we do. Because this is a square plus the derivative of UR square. Right? Because the derivative of UR square is 2 times U times this, which was the derivative of UR. So I get that the derivative of this is equal to a nice square plus the derivative of someone. One that I put this someone here on the beginning, and I get that this quantity is monotone. Okay, so this means that the derivative in R of this minus UR minus this is really a square, which is not negative. And this is what we wanted. Okay, so this is what happens for the obstacle problem. But then for the Bernoulli problem, it's really the same kind of computation. Okay, so for the Bernoulli problem, you can try to do it as an exercise, and it's nice that you take the functional, you rescale it, you get something like that. You still have this property. The UR, now the derivative is the same without the 2. And then you compute really the derivative of the energy at scale of at UR. Okay, the derivative at R equals 1. You compute, and then get something like this, a square plus the derivative of someone. So you put the someone at the beginning, and then this is a monotonicity formula. So this is nice because you get a monotonicity formula just by trying on the most natural quantity, which is the energy of UR. Okay, but you have to modify it a bit. So notice that for minimal surfaces, so the idea of taking the energy of UR comes from minimal surfaces, because in that case, it's really, you take the perimeter of the minimal surface in BR, rescaled by the natural power, and this quantity is monotone without any modification. While here, for these two free boundary problems, you take this energy, this is not monotone, but a small modification makes it monotone. So this is the monotone quantity in our context. Okay, so remember, this monotonicity formula is used basically, most importantly, to prove that blowups are homogeneous. Okay, which is what we said before. So we have some common properties in both problems, and basically the first property is that the problem is scale invariant, right? So we found, thanks to optimal regularity and non-degeneracy, we have some scale invariance, which means that we can consider rescalings. So if U is, say, a minimizer or a solution as in this picture, then we rescale from BR to B1. And then if U was a minimizer in BR, then UR, this rescaled function, is a minimizer in B1. Okay, and then in this picture, of course, I pictured it as if the free boundary was smooth. If this was smooth, what you expect is that this becomes flat, right? When you rescale a smooth surface, this becomes very flat. But this, we still don't know this, right? A priori, this could be a disaster, and then here we would see only a disaster. But okay, this is the picture to have in mind. This is what we know is that the problem is scale invariant. And moreover, UR has an infinity norm comparable to 1. And this is thanks to optimal regularity and thanks to non-degeneracy. Then the second thing that we have is that, that we have convergence of UR up to subsequences, but we have convergence of UR to the blow-up U0 locally uniformly in all of our N. So moreover, U0 will be a global solution or a global minimizer, depending on if we are in the obstacle problem or the Bernoulli problem, right? But in both cases, we can consider blowups. Okay, so this is nice. And then thanks to a monotonicity formula, which is what we just did, thanks to a monotonicity formula, blowups are homogeneous. Okay, so these blowups U0, so they not only they solve the equation or they are minimizers of the energy functional, but thanks to a monotonicity formula, they are homogeneous of degree 2 or of degree 1, depending on which of the two problems we have. So these are the common properties. These are the common properties of both problems that we could prove basically at the same time, even if some proofs are different. But this is really parallel, and the theorems are very analogous in both cases. Okay, so in both cases, we have that the problem is scale invariant, that we can consider blowups, that blowups are homogeneous, that we have a monotonicity formula, that we had optimal regularity and non-degeneracy, etc. Okay, so all this can be seen as a parallel theory for both problems. But now the next question is, can we classify blowups? Okay, and then it's here where we will see that the two problems are really different, because not only the techniques, but even the result, the classification of blowups will be completely different in one case or the other, in the obstacle problem or in the Bernoulli problem. Okay, so this is why I will treat both problems now separately. I will first present the Bernoulli problem, then the obstacle problem, and see what is known in each case. Okay, so then the next step, if we think about minimal surfaces, as I said before, we need not only the classification of blowups, but then we need also, if we can prove that blowups are flat, say that, so that this happens as in this picture, that in the limit we get something flat, then we will need a theorem that says that flat implies C1 alpha. Okay, and then we will need a separate theorem that says that once you are C1 alpha, then you are really C infinity. Okay, so all these are separate theorems that will be different in the obstacle problem and in the Bernoulli problem. And then especially in the classification of blowups, as I was saying, the two problems are really different. Okay, so if I still have some like 5-10 minutes, then I will start with the classification of blowups, and then we will continue. Of course, I will not finish now, but we will continue next day. Okay, so basically for the classification of blowups, we start with the Bernoulli problem, which is the most similar to minimal surfaces, actually. Okay, so the result and the theorem and the spirit, in a sense, is more similar to minimal surfaces, and then the obstacle problem is a bit more different. Okay, so for the classification of blowups, well, what do we have? The blowups satisfy this, that they are harmonic whenever they are positive, that the gradient has constant modulus on the free boundary. So gradient is modulus 1 on the free boundary. So this is the PDE satisfied by U, which goes well with the limit. And then in the limit, you get this. And the extra information we have is that U is one homogeneous. Okay, so we have a one homogeneous function satisfying this. Okay, now what else? So let's start with dimensions. So we can start with dimension 1, then we go to dimension 2, and then we see to what extent we can go up in dimension and still prove some classification of blowups. But first, to understand the problem and see really what happens, it's good to look at dimension 1. Okay, so this is of course the simplest case, but then we have two possible solutions only, because we have gradient norm equals 1, modulus of gradient equals 1, and then harmonic. So a harmonic function in 1D is really a line, is a linear function. So this is one option, okay, which is the positive part of X, but it solves these three conditions, it satisfies these three conditions. And then this is the 1D solution that we expect at free boundary points. Okay, so this is really 0 on a side of the free boundary point, and then really a linear function on the other side. This is what we expect, and this is what I call the 1D solution. Okay, and the only other option, like if you formally look at this, it could be that you have this kind of like the absolute value of X. But this is really not a solution, not even a critical point of the energy function. Okay, so even if you can formally put this here and it satisfies this, this is not a solution when you look at the energy functional. So you can really discard it. Okay, so in dimension 1, this is almost trivial, but at least we know what to expect. Okay, so this is not an admissible, not even a critical point for the energy functional, so we discard it completely, and then the only possible solution is this one. Okay, now let's look at the most interesting case, which is dimension 2. Okay, so this is much more interesting because it's much less obvious. Okay, but we can still classify it fairly easily. Okay, so any solution will be of this form. So basically, by homogeneity, the zero level set will be a cone in 2D. Any cone in 2D could be a possibility. Okay, so you could have something like this. You could have even infinitely many connected components of U being positive. I mean, you could have really as many components as you want here, but it's always like this. So there are, I mean, really some sectors in which U is positive, and then some sectors in which U is 0, and that's it. And you have to, I mean, fill the full space. Okay, and the origin is of course the special point in which everything is homogeneous with respect to the origin. Now, what can we do if we have something like this? Well, because this is a PDE, I can look at this PDE in each of these small cones, right? Because in each of these small cones, U is 0 on the boundary and U is positive here in the interior. So they don't talk to each other, because in R2, a cone like this disconnects solutions. So this is disconnected from this, which is disconnected from this, etc. So I can look at each of them separately, which is good. Okay, so this does not happen in higher dimensions. And now, if we look at each connected component separately, what do we have? Well, we can try to understand what happens with positive harmonic functions in cones. And this is what happens. Given any cone in Rn, there exists a unique function which is harmonic, 0 on the boundary, and positive in the interior. Okay, this is an easy, I mean, this is a well-known fact about harmonic functions. Not easy, but well-known. And then, moreover, it is homogeneous of a certain degree lambda that depends on the cone. Okay, and moreover, this homogeneity is monotone on the cone. So if you take a larger cone, the homogeneity will be smaller. Okay, so there is a monotonicity of the homogeneity with respect to the cone. And then in 2D, like if you have two cones like this, well, then either one is bigger than the other or they are equal. I mean, there is really nothing else. I mean, you cannot have strange things if you have connected cones like these ones. Okay, so for each of these cones, we have a harmonic function which is positive inside the cone and it's homogeneous of degree 1. So we already know the homogeneity. We already know this lambda. So this must fix the cone. Okay, and this is indeed what we see. So simply by using this on each of the connected components, we see that each of the connected components satisfies these three properties with homogeneity 1. But now, if you have homogeneity 1, the only cone with homogeneity 1 is the half space. Okay, because the half space, this solution is really the positive part of, I mean, it's really a linear function in the case of the half space. So half space has homogeneity 1. It means that any other cone has homogeneity either bigger than 1 or less than 1, depending on if the cone is bigger or smaller. But this means that each of these connected components has to be a half space, and there is nothing else that can happen. You cannot have connected components different from a half space. Okay, and this is simply by looking at harmonic functions in cones, because in 2D, cones are very simple, in a sense. I mean, totally, there are no strange things that could happen. Okay, but then each connected component is a half space. What happens then? Well, it means that only two things can happen. You are basically in a 1D situation. So either you are this 1D solution, or you could be something like this, but we said already that this cannot happen. So the only possibility is really a half space. So the only possibility is for a fixed vector on the sphere E, you have the positive part of a linear function like this. So x dot E, take the positive part, and this is the classification of blowups. So this is really all that can happen in 2D. Okay, so this completely classifies blowups for the Bernoulli problem in dimension 1 and in dimension 2. Okay, and here we only use the PDE really. So next, well, tomorrow we will see, in the next lecture, we will see what happens in 3D, and we will see that 3D is already much more complicated. Okay, so the result in 3D, one can still classify blowups, but you need to use much more strong tools, and the result is much more deep in a sense. Okay, so I will stop here.